Welcome to the flock. Let's dive into some introduction of thermochemistry by exploring exothermic reactions and endothermic reactions, along with calculating for joules, which is a unit of heat energy. Stick around to see how cool thermochemistry can be. If you've never experienced the joy of opening up a hot pack, check out what's inside. I just put a little bit of it on my hands so that you can see. So that chemical you just saw was iron in its solid form. Now, in order to activate a hot pack, you have to remove it from its container and you have to shake it around really vigorously. So you shake it, shake it, shake it, shake it. Why are we shaking it? We're shaking it so that we can expose it to oxygen in the air, the gas form of oxygen. And when that happens, a chemical reaction occurs that forms iron oxide in its solid state, which is just rust, by the way, and it also forms heat.
That's the whole reason we use it to begin with, to heat up our hands.
Now, at room temperature, this hot hands was around 25 degrees Celsius, and after being opened and exposed to the oxygen in the air, it's pretty difficult to see, but that's already at 45 degrees Celsius. Now, when we actually look at this chemical reaction, and we see that on the reactant side, we had iron separate from oxygen, and on the product side, we have those two atoms mashed together. Iron and oxygen formed a bond. So in this reaction, we can say that a bond was formed. This is important to remember because we're going to be coming back to this premise chemically throughout the entire thermochemistry unit. So please keep in mind that when we are producing heat, like in the case of hot hands, we are going to be forming chemical bonds. So just like we did with the hot pack, let's check out the cold pack. Inside, we have a little packet of water. Ta-da! That's the water there in its liquid form. And the rest of the slurry inside there is our ammonium nitrate salts. That's this guy right here in its solid form. Now, when we add heat to this system and we squeeze together right here to pop that water packet and shake this, what happens is we end up dissolving our ammonium nitrate salts in the water that's now released from the packet that we pop. And we end up with products that are separated from each other in its cation form for ammonium and the anion form for the nitrate. So in the case of the cold pack chemistry, we can say that on the reactant side, the chemical was together, but on the product side, they're separate. Therefore, we can say that bonds were broken. So in other words, when a chemical reaction feels cold, when it requires heat for it to happen, we have chemical bonds breaking. So we obviously want to name these two different reactions where one releases heat or produces heat and one requires heat or absorbs heat. We need to come up with an actual chemical name for these. Using this word bank up here, pause the video and see if you can figure out what each one would be called. Hopefully you realize that for the hot pack, there was heat flowing out of the system. Therefore, we call this an exothermic reaction. And as you recall, for the exothermic reaction, we had iron come together with oxygen to form iron oxide, i.e. rust. And that means that we form chemical bonds whenever we have an exothermic reaction. Anytime a reaction produces heat or it feels hot, we call it exothermic due to the formation of bonds. All right then, how about the cold pack? Well, we know that the cold pack required heat on the reactant side, meaning that it absorbed heat energy. That means that the heat went into the system. We call this endothermic. And if you recall the chemical reaction, we had ammonium nitrate dissolve in the water to break those bonds and form ammonium cation and nitrate anion in solution. So anytime we break chemical bonds and a reaction feels cold, we call that endothermic. So we talked about this one releasing heat and this one absorbing heat. But what are the units for heat anyways? We're going to use the unit of joules. And now joule is defined as the amount of energy to push with 1 Newton of force for 1 meter, but we're going to use this in reference to water. We're going to say that it takes 4.184 joules to heat 1 gram of water by 1 degree Celsius. I find that it makes more sense to remember this as a conversion factor. there's 4.184 joules per 1 gram of water to increase 1 degree Celsius. Just as a reminder, we're also going to be dealing with kilojoules, kJ, and that's equivalent to 1,000 joules, and also calories, which are equivalent to 4.2 kilojoules. Let's do a little practice with this calculating for joules. If I had a single tea-light candle and I placed it underneath a cup of 18 grams of water, and that candle managed to heat the water from 23 degrees Celsius to 25 degrees Celsius, that's a difference of 2 degrees Celsius, how many joules of energy was required in order to do that? Well, we're going to start with our given, 18 grams of water. And we know that our conversion factor is 4.184 joules per 1 gram of water. So let's go ahead and match up our units so that they cancel by putting the 1 gram of water on the bottom and the joules on top. Now, mind you, this only works here because we're dealing with water. If there's a different chemical, you cannot use this conversion factor. It's specific to water. Here we see the grams of water cancel, and now all we have to do is multiply 18 by 4.184 joules to get 75.312 joule. We're not quite done yet. Remember that this would be the amount of energy to just raise it 1 degree Celsius. However, our question raised it 2 degrees Celsius. So the last step here is just multiplying this answer by 2. Then you can see that the total amount of energy required to do this is 150.624 joules. Now that you've seen me do it, go ahead and pause the video here and see if you can solve for the number of joules for this calculation. Keep in mind that you're going to need to convert your kilograms to grams before you can solve. Ready, go. All right, let's check your answer. So hopefully this is the answer that you got right here, 269,219.48 joules. So now that you can calculate for heat using joules as the unit, what is heat anyways? We know that heat is energy, we call it heat energy, but what is that? The idea here is that when molecules get more heat energy, they move faster. And when molecules lose heat energy, they move slower. In other words, were the molecules in the hot pack moving fast or slow? So hopefully you would recognize that the molecules in the hot pack are moving fast, and that's what gives that hot temperature reading. And the molecules in the cold pack are moving slow, and that's what also makes it read as a cold temperature on the thermometer. Okay, but what was producing the heat? Recall that in the hot pack, we formed a bond. We made a bond between iron and oxygen. That formation of the bond is literally what produced heat energy. Now think about that for a second. Literally at a molecular atomic level. All of those little atoms coming together and forming bonds between the iron and oxygen caused that heat. That's mind-blowing, I think. And this one feels cold because it's literally absorbing heat. It feels cold to us because there's heat going into the system instead of out of the system. And we perceive that as cold due to the breaking of chemical bonds. So now you heard me use the word heat and temperature. There is a distinct difference between those two things, and you should know the difference between them. This is where a lot of my chemistry students got a little confused. So let's go into depth here on the difference between temperature and heat. Temperature is the average kinetic energy of a sample. So if you stick a thermometer in a sample and it gives you a reading, it's telling you the average motion of those molecules. What's the average kinetic energy? Read back to you as a value in temperature. Whereas heat is the sum or the total kinetic energy of all the molecules combined. In other words, if you had a bucket at 20 degrees Celsius and a drop of water at 20 degrees Celsius, even though they both have the same temperature, the bucket would have the greater heat because it has more molecules than just a single drop measured at 20 degrees Celsius. And now the great thing about heat is that you can transfer it to another system. You could dump that bucket of 20-degree water and heat up 10-degree water, whereas one drop of 20-degree water would make literally no difference to a 10-degree water bath. And heat takes into account the mass of all those molecules present and the speed in which they're going, hence the kinetic energy. I think the difference between heat and temperature is also easier depicted with some pictures.
Few moments later.
Let's take a look at this bucket versus teacup example. Let's say we stick a thermometer into both of these, and we see that the teacup has water at 100 degrees Celsius. That's its temperature. And the thermometer in the bucket reads 50 degrees Celsius. Again, that's the temperature of the bucket. So even though the thermometer or the temperature of the teacup is bigger and the bucket's temperature is lower in comparison, there are more water molecules in the bucket at 50 degrees Celsius, so that means the hotness or the heat is greater, whereas the teacup has a lesser number of water molecules present at 100 degrees Celsius temperature, therefore its heat is less. In other words, when we think about temperature, we're literally just going to be thinking about the degree of hotness. Whereas if we're considering heat, we're going to be thinking about the quantity of hotness. Let's think about this in one other way. What if instead of water, the bucket was filled with $50 bills? Remember, it was at 50 degrees Celsius, so let's just replace that with $50 bills. And I'm talking like filled to the brim, overflowing with $50 bills. And the little teacup was filled with $100 bills. And I offered you to take one of these options. Which one would you pick? Hopefully, you would pick the bucket full of $50 bills, because even though the $50 bill itself is less than a $100 bill, there's way more $50 bills, which means that this bucket would be raking in some serious dough for you. Think about how hot the bucket would make you feel when you think about all the stuff you're gonna buy. The bucket has increased heat due to the sheer number or quantity of molecules present at a certain temperature. So this whole idea of heat in terms of absorbing heat energy or releasing heat energy by breaking chemical bonds or by making chemical bonds is the entire premise of thermochemistry. In this lesson, we talked about how chemical reactions that form chemical bonds will release heat energy, and we call those exothermic. We also talked about endothermic reactions, which are those that break chemical bonds and absorb heat energy. We were then able to calculate using the units for heat, which happens to be joules. 4.184 joules can raise 1 gram of water by 1 degree Celsius. And then we further saw the difference between temperature, which is just an average kinetic energy measured with a thermometer, versus heat, which is the sum or total kinetic energy of all the molecules within that system, which is the reason why a bucket of 50 degrees Celsius has more heat than a teacup of 100 degrees Celsius water. Before we move on to more calculations in thermochemistry, make sure that you can fill in those blanks very confidently to know which reactions break bonds, form bonds, and which ones absorb or release heat energy. And also, what are they called? Make sure that you could answer this question again without looking back through the video. And if you want to check your answer, go ahead and comment below. I'll be happy to let you know. Please give this video a quacks up and subscribe to Duckonta for some more free educational content. And now you know why thermochemistry is super cool and why I'm so hot about it.
No guts, no glory.